Talk about linear versus nonlinear analysis. One of the key assumptions we make for many simulation studies is that our analysis is linear. I want to go into some detail on when this assumption is valid and when it's not. The basic equation used in finite element analysis is force equals stiffness times displacement. In a linear analysis, the stiffness matrix is constant, and so as long as this represents our problem, we're okay with the linear assumption. But if the stiffness changes during loading, a linear analysis is no longer valid. Now, the stiffness matrix is dependent on both material and geometry, and so these are the two main sources of nonlinearity that we need to look out for. Let's talk about material nonlinearity and start off with a bit of review on stress and strain. What is stress? Engineering stress is defined as force over area. Stress values are useful because they represent internal forces independently of overall part size. And what is strain? When we stress material, it's going to stretch. Engineering strain is the ratio of change in size divided by the initial size. Of course, larger stresses mean larger strains and vice versa. For many materials, the relationship between stress and strain is linear and defined by the material's elastic modulus, also called Young's modulus, which represents the slope of the stress-strain curve. This linear relationship is maintained until the yield strength of the material is reached. Up to this point, the material behaves elastically, meaning if we remove the load, the part will return to its initial shape. Beyond this point, the post-yield relationship is no longer linear, and further loading will result in plastic deformation. Also, some materials are inherently nonlinear and don't exhibit a linear region at all. In either of these cases, our linear material assumption is not going to be valid, and a nonlinear material model is going to be needed. The second potential source of nonlinearity is the geometry. In a linear analysis, calculations are based on the initial geometry, and this is valid as long as any change in shape is very small. However, if there is enough deformation to cause a significant change to the stiffness of the part, again, this is a situation for a nonlinear analysis. So let's quickly sum things up in context of SOLIDWORKS. SOLIDWORKS offers finite element analysis in a number of different packages, all of which include linear static analysis. Linear analysis is valid as long as the stiffness matrix is constant, and luckily for us, this represents many engineering problems. Otherwise, we're looking at a nonlinear situation and SOLIDWORKS simulation premium. The main sources of nonlinearity are nonlinear material behavior, either post-yield or an inherently nonlinear material, and large deformations. I hope you